discussing about the AC voltage applied to a resistor, inductor, capacitor we have done, and also I have done the power supply to resistor, inductor and the capacitor. We have already done that part. I have given you as a homework that you have to try by yourself how to calculate the power supplied to a capacitor, that you have to try by yourself. Now what I am going to do, I am going to combine the inductor, capacitor and the resistor, which is also called as a Lcr circuit. Okay, so this is a Lcr circuit. Inductor, capacitor and the resistor. This is a resistor, okay, connected with an AC voltage. So as we know, this is a series connection. So if it is a series connection, voltage across inductor, voltage across capacitor and voltage across the resistor, these three will be different. And if I add all the three voltages, what I'll be getting? I'll be getting the total voltage, that is this. Now we need to go back a little bit because we have done the phasor diagram. By using a phasor diagram, we'll be finding a relation here. Remember, when we have done the resistor part, AC voltage supplied to a resistor, the voltage equation that we have got, this was this equation. And the current equation we have got is for the resistor, it was I is equals to I naught sin omega t. This is for resistor. For the inductor, it was I is equals to I naught sin omega t minus pi by 2. This is for the inductor. And for the capacitor, we have got I is equals to I naught sin omega t plus pi by 2. So these are the equations that we have got. And also we have drawn the phasor diagram. By comparing the voltage and the current, these two are in same phase. Here voltage and the current both are in out of phase, and it is having a phase difference of pi by 2. This is also having a phase difference of pi by 2, but here is current is lagging behind and here the current is leading. Okay, so that is the difference that we have done in the AC voltage supplied to a capacitor, inductor and the resistor. So let us first see the voltage across the inductor. It is given as VL is equals to I into XL. I into XL means I into resistance. XL is a inductive reactance. That I have already done it. VR will be equals to I into R. And VC will be I into XC. These all are following the same Ohm's law only. Okay. Capacitive reactance, resistance and the inductive reactance. These are the voltage, that is VL, VC and VR. Now as we go by the phasor diagram, voltage and the current in a phasor diagram for the AC voltage applied to a resistor, they are in same phase. So if I draw the phasor diagram for this, the voltage across the resistor and the current will be in the same phase. That means both are will be in the same line because they are in the same phase. Then if I compare this current as a reference for all, okay, as a reference for all, this current will be fixed for all. Okay, I will be taking this as a reference. Now here you see, for the current across the inductor, the current was lagging behind by pi by 2. Current was lagging behind by pi by 2. That means voltage is leading. How much the voltage will lead? Voltage will be leading by pi by 2. So your voltage across the inductor will be represented here. This will be having an angle of pi by 2. You can see voltage and the current are having a phase difference of pi by 2. Same way, if I compare with the capacitor, this is a current across the capacitor. You can see the current was leading by pi by 2. That means your voltage is lagging behind by pi by 2 for the voltage across the capacitor. Clear? So what we need to do, current, you don't change the place of the current, will be changing only the place of the voltage. So the voltage across the capacitor will be here. This is VC. Okay, VL, VC and here it is your VR. Now we need to add the total voltage. For calculating the total voltage, you can see all the vectors are in different position. These are all vectors. VL, VC, VR are in different position. Here, because these are co-initial vectors, we can use the parallelogram law of vector addition. But for that, we have to reverse one vector. I will be reversing this vector VC. So if I reverse the vector Vc, so it will be minus of Vc. Then we can add with this vector. This you have already got in class 11 vector addition. So here this will be represented by VL minus of Vc. If I add the vectors, then according to the parallelogram law of vector addition, if this is one vector and this is one vector, resultant will be represented by its diagonal. Yeah, so this will be the resultant, that means the total voltage. So I'll be making a parallelogram of this one. Yeah, if I make a parallelogram of this one, then after using the parallelogram law of vector addition, what I can write, you see, V is equals to, according to parallelogram law, V is equals to root over VL minus of Vc whole square plus VR. It will be VR whole square plus 2VL minus of Vc into VR cos 90. This will be 0. So only the left out part will be this. So VL minus of Vc whole square plus VR whole square. Now I can place the value from equation 1, 2 and 3. So if I put from equation number 1, this will be IXL minus it will be IXC whole square plus of I square R square. From here I can take I as common. So this will be I square from here and I square is already there. I'll be skipping one step. I'll be putting the I directly outside of the root. So it will be XL minus XC whole square plus R square. This will be equals to V. If I put the E on the left hand side, okay, if I put the E on the left hand side, then what will I get, you see? It will be V by I equals to root over XL minus XC whole square plus R square. So V by I is called as Z equals to XL minus of XC whole square plus R square. Okay, so this Z is called as the impedance of the circuit. And what does the impedance represents? Impedance represents the total resistance offered by inductor, capacitor and the resistor. This is called as a impedance of the circuit. And this we have got the total resistance for the Lcr circuit. So some more topics related with this chapter we'll be discussing in the next class. Thank you.